Let's talk about another very important series called the Harmonic Series. So the series is so important, I'm going to highlight it, the Harmonic Series. And its representation looks really simple. The general term is just 1 over n. So if you take a look at this series, we want to show in example 11 is we want to show that this series diverges. Now, to show that this series diverges, we're going to look at a subsequence of the partial sums. So let's not worry about this particular subsequence yet. Let me tell you what I mean by a subsequence. Now, to describe the idea of a subsequence, I'm going to pause the video and write out many terms of a sequence. So hold on for 1 second. Voila, you see that I've written out 12 terms of a sequence. And when I say subsequence, I just mean any sequence that's contained within this sequence. So, for example, I could take every other term, every even term like this. And if I were to do that, A2, A4, A6, A8, A10, A12, that would be an example of a subsequence. Let me undo this. I don't just have to take every other one. I could say something like, let's take every third one. So I'll take the first one, I'll take the fourth one, I'll take the seventh one, I'll take the 10th one. This would be another subsequence. It's just a sequence contained within your overall sequence. Okay? And one of the things that's true is that if a sequence AN converges to 0, then every subsequence also converges to 0, right? Because if you found some infinite subsequence that didn't go to 0, that would violate the sequence going to 0 overall, okay? If you were to look at a picture, a picture might look something like this. Voila, you suddenly see a number line with a bunch of dots appear. And what I'm trying to do is I'm trying to illustrate a situation where it looks like my sequence is trying to go to 0, but somehow I have some subsequence, in this particular case, every fourth entry, that isn't going to 0. And what I'm trying to convince you of is even if you try to repeat this pattern, you know, most of it looks like it's going to 0, but there's still always a part of it that refuses to go to 0. So this would be an example of a picture that diverges. Okay, so what I'm saying here is that each of these dots are going to represent parts of our sequence of the nth partial sums. And what we want to do is we want to actually, we're not even going to look at all of these dots. We're just going to look at a subsequence. We're going to look at, a certain collection of dots, and we're going to show that this collection of dots does not tend towards 0. And that will show that our sequence is going to diverge. So what is the subsequence we're going to look at? Well, we're going to look at this subsequence right here, S sub 2n. Okay, so I'm going to scroll up and we'll continue this discussion. Okay, so let's look at this sequence, S sub 2 to the nth power. So basically we are taking a look at, we're going to look at all the terms that are powers of 2. Okay, so why don't we write out what those terms are? So the first term is going to be S2, right? That's the first term of our subsequence. That's just going to be 1 plus 1/2, the sum of the first two terms. Let's look at S4 next. S4 is 1 plus 1/2 plus 1/3 plus 1/4. Okay, and what I'm going to do is I am going to compare uh, this partial sum right here. I'm actually going to take something that's a little bit smaller than it. In other words, if you look at this 1/3 over here, this 1/3 is bigger than 1/4, right? Because the denominator is smaller. So what I can do is I can say, you know what, this is bigger than 1 plus 1/2 plus 1/4 plus 1/4. And that thing sums up to 2, right? Okay, so let's take a look at the next term. The next term will be the next power of 2, which is 8. So we have S8. What does S8 look like? S8 is going to look like 1 plus 1/2 plus 1/3 plus 1/4 plus 1/5 plus 1/6 plus 1/7 plus 1/8. Okay, and what I can do is I want to do the same thing that I did before. So earlier, I sort of took this part right here and I rewrote that as sort of 1/4 plus 1/4. And I want to do the same thing for this guy. So I'm going to kind of group these two guys together. And then I'm actually going to group these 4 over here together. And I'm going to come with a series that's, you know, a little bit less than S8. So S8 is going to be bigger than 1 plus 1/2 plus, and then I'm going to put in parentheses here, 1/4 plus 1/4. Okay. So I made, obviously, 1/4 is less than 1/3. And then for the second set of parentheses, I'm going to have a plus. I'm going to replace each of those with a 1/8. So it'll be 1/8 plus 1/8 plus 1/8 plus 1/8, like this. And then I kind of put parentheses around there like this. So the purpose of the parentheses is just to make it clear what I'm talking about. So all of these, the sum of these guys is certainly less than the sum of these guys because this fraction is bigger than this one's bigger than this one's bigger than this one, right? So what happens when you add up each of those guys? This is 1 plus 1/2. Here's another 1/2. And here's yet another 1/2. So we really get 1 plus 3/2. So this is equal to 1 plus 3/2. Now, when I wrote my S4 example, instead of simplifying it, I think I should have left it as 1 plus 2/2 because it's a little bit easier to see the pattern. Okay, so what is the pattern that I would like for you to see? Well, look, S2 is 1 plus 1/2. S4 is 1 plus 2/2. S8 is 1 plus 3/2. I hope you could see this pattern. Let me highlight it over here. That numerator is steadily increasing by 1. So if I were to look at the next term of the subsequence, S16, that's going to be bigger than 1 plus 4/2. And if I were to look at the next term of the subsequence, S32, that would be bigger than 1 plus 5/2. And you look at the next one, S64, that would be bigger than 1 plus 6/2, right? So I hope you can see the pattern. We can always look at our subsequence and we can see that we have a lower bound for each of those terms of that subsequence. So let me scroll up a little bit here and let me try to draw a conclusion. All right, so this investigation should lead us to the fact that this subsequence s to the 2n is going to be greater than 1 plus n over 2, right? 64 is 2 to the 6th, 32 is 2 to the 5th, 16 is 2 to the 4th. So we can say as n goes to infinity, this n over 2 is also going to go to infinity. This means that my subsequence s to the 2n is going to infinity. So we have some subsequence that's not going to 0. In fact, it's the opposite. It's going to infinity. So this tells us that our series, the harmonic series 1 over n, as n goes from 1 to infinity, this series diverges. And this is a very key result for us. The reason why it's key for us is we want to have a bunch of series that we know and understand, like the geometric series or like the harmonic series, so that we can use this series to test whether other series converge or diverge. That's something we're going to do in subsequent sections in this chapter. And this concludes this particular video lecture on the harmonic series. Take care, everyone.